This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll be discussing about digital logic gates and the exclusive OR gates and universal gates. So the various types of logic gates we are going to see in this lecture. So the today's topics are logic gates, its symbols and truth tables. And also we'll see what are the universal logic gates and why they are so called, and why NAND and NOR are called as universal logic gates, and we'll see the applications of universal logic gates in this lecture. So first of all, let us see what is a logic gate. Logic gates are the basic building blocks of digital systems. Any digital system is constructed or is implemented using logic gates. So that is why we will always call these logic gates as basic building blocks of digital systems. So it is an electronic circuit having one or more inputs and only one output. So a logic gate may have either one input or more than one input, like 2 or 3, and number of inputs also it may have. But the output of a logic gate is only one. So as it is a basic building block of digital systems, so it always accepts the inputs and also produces the outputs in the form of binary ones and zeros. The relationship between the input and the output is based on the logics which is performed by certain logic gate. Based on this, logic gates are named as AND gate, OR gate, NOT gate. As you all know that AND, nothing but logical multiplication. OR is nothing but logical addition, and NOT is logical negation, that is complementation. So these are the names basic gates, and the names of the basic gates are AND, OR, NOT, where OR AND performs logical multiplication, and OR performs logical addition, and NOT performs logical negation, or else we can also call it as complementation. Or else it will get the complement of the given input signal. A logic gate is a digital gate that allows data to be transferred. Logic gates use logic to determine whether or not to pass a signal. So, passing a signal means the output of that particular circuit is 1. So, not passing a signal means the output of the circuit or else a gate will be 0. So, depending on the logic, it determines whether the signal is to be passed or not. Logic gates, on the other hand, govern the flow of information based on some set of rules. So, based on some set of rules, it governs the flow of information from input to the output. So, this is a basic introduction about logic gates. So, we have various types of logic gates. So, these are the various logic gates which are commonly used. Those are AND gate, OR gate, NOT gate, NOR gate, NAND gate, XOR and XNOR. This is also called as exclusive OR. And this is XNOR is also called as exclusive NOR. So these are the commonly used logic gates. AND gate. First of all, we'll see the operation, the symbol and the truth table of each and every gate. So first we'll start with AND gate. An AND gate has a single output and 2 or more inputs. So that means the minimum number of inputs required for this AND gate are 2. So even we can have more than 2 inputs also, but the output is only 1. So the output of this AND gate is 1 when all the inputs of the AND gate are equal to 1. If any one of the input is 0 or all the inputs are 0, then the AND gate output will be 0. That means AND gate produces a logic 1 as output when all the inputs of that gate are equal to logic 1 or high. If any one or all the inputs are 0, then the output of the AND gate will be 0. So the AND gate's Boolean logic or Boolean expression can be expressed as Z is equals to X dot Y. So as we all know that AND operation is represented with dot operator, whereas OR is represented with plus operator. So that the Boolean expression for AND gate is Z is equals to X dot Y, where X and Y are the inputs. And this is a logical symbol, so which is performing the logical AND operation. But we will not use this symbol in our practice in digital circuits. We always represent that Boolean function for AND gate as X dot Y. Z is equals to X dot Y, where Z is the output and X and Y are the inputs here. So this is the logic gate, AND gate symbol here. So which is having 2 inputs and 1 output. Even if I have 3 inputs, the symbol is like this. So if I have WXY, then Z will be equals to W dot X dot Y. So this is the AND operation. Coming to the truth table. So as you all know that truth table will give you the, will list the output of a circuit for all the possible combinations of inputs. So here, as we have 2 inputs, we can have 4 combinations for the input, because all these inputs are binary inputs. So binary inputs may be either 0 or 1, and hence we can have 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. And AND operation it is performing. So it is nothing but logical multiplication. 0 dot 0, 0 multiplied by anything is 0. As I told you, if any one or both the inputs are 0, the output of the AND gate is 0. So as both the inputs are 0, the output is 0. As one input is 0, the output is 0. 1, 0, Y is 0, and hence output is 0. When both the inputs are equal to 1, then only AND gate produces logic 1. So that is why the output is 1. So this is about the AND gate, and it performs the logical multiplication operation, and it is represented with dot operator. Now coming to the OR gate. So it is also having 2 or more inputs and 1 output. So that means the minimum number of inputs required for this OR gate is also equal to 2, and even it can have more than 2 inputs also, but the output is only 1. And coming to the output of this logical OR gate, so it produces the output as 1 when any one input or all the inputs of the OR gate are equal to 1, then the output of the OR gate is 1. If both the inputs are 0, then only the output of the OR gate becomes 0. So this is the logical OR operation. So next up, the OR gate's Boolean function is given by Z is equals to X plus Y. Z is equals to X plus Y. So where X and Y are the inputs, where plus represents the OR operation. That is logical OR operator. And this is the symbol here. This is a 2 input OR gate, X, Y and Z. And this is the logical, this is to represent logical OR, but always we represent Z is equals to X plus Y. Okay, in order to show that logical OR, this is a symbol for logical OR. So that is nothing but addition here. So Z is equals to X plus Y. And coming to the truth table, so when both the inputs are 0, then only the output of the OR gate is 0. If any one input or both the inputs are 1, the output of the OR gate is equals to 1. So this is OR gate. Now coming to the NOT gate. So as I told you that NOT gate performs the negation, logical negation, or else complementation. So the NOT gate is basically a single input gate, and it is having one output. So coming to the operation, when the input of the NOT gate is 1, the output becomes 0, and vice versa. That means if the input is 0, output is 1. If the input is 1, output is 0. That means it just simply complements the input signal. A NOT gate is sometimes also called as an inverter, because it inverts the, or else it complements the input signal and produces the output. So coming to the logical expression, so the inversion can be represented with complement. Y is equals to X complement, where X is the input and Y is the output. Even we can also represent Y is equals to X bar. So that means bar or this single quote or complement operator will represent the NOT operation. So this is the NOT gate symbol. So we have a bubble. This bubble indicates complement. So always you remember, wherever we have a bubble, it means that the signal is getting inverted. So this is the output and it performs the logical negation. So always you remember y should be represented with x complement or x bar. Okay. So coming to the truth table. So as it is a single input gate, one input we have, so only two combinations. That means that input may be either 0 or 1. If the input is 0, output is 1. If the input is 1, output is 0. So this is NOT gate. Now coming to the another gate, NOR gate. So NOR gate is also known as NOT OR gate. That means NOT of OR gate. So OR gate followed by a bubble is nothing but NOT gate. So as I already told you that this bubble always indicates NOT. So OR gate with a bubble at the output side indicates the NOT gate. So that is why we can also call it as NOT OR gate and consists of an OR gate followed by a NOT gate. So even this symbol is equivalent to OR gate followed by a NOT gate. So this is the NOT gate. So the minimum number of inputs required for this NOR gate are 2. Again we can have even more than 2 inputs also, but the output is only 1. And the output of this, as it is complement of OR gate, so we can say that the output of NOT gate is 1 only when all the inputs are zeros, and when any one or all the inputs are high, then the output of the NOR gate becomes 0. So this is the output of the NOR gate, and the expression for NOR gate is given by z is equals to x plus y whole complement, or else we can also write this one as x plus y whole bar, where x and y are the inputs and z is the output. So this is the symbol. OR gate with a bubble is nothing but NOR gate. Coming to the truth table here, as it is minimum in number of inputs required are 2. So I am taking the 2 input NOR gate here. So as I have 2 inputs, 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. So according to the definition or else according to the operation, so NOR gate produces the output as 1 when both the inputs are equal to 0. So when both the inputs are 0, it is 1. And if any one of the input or all the inputs are equal to 1, the output of NOR gate is equals to 0. So this is the NOR gate operation. Now coming to the NAND gate. NAND gate sometimes is also known as NOT AND gate, and it is essentially a NOT gate followed by an AND gate. So this is a symbol here. This is a inverter and we have a NAND gate. NAND gate with a bubble at the output side indicates the NAND gate, or else this is also equivalent to we have an AND gate with an inverter at the output side, A, B, C. So this is AB and this one is AB whole bar, or else A dot B complement. So this is the NAND gate output. So now coming to the, as it is a complement of AND operation, when the AND gate output is 1, when both the inputs are 1, then only the output of the AND gate is 1. It is reverse. So when both the inputs are 0, when both the inputs are 1, then the output of the NAND gate is 0. If any one of the input or all the inputs are equal to 0, the output of the NAND gate becomes 1. So that is the operation of NAND gate. Coming to the expression, z is equals to x dot y whole complement. So as we have all, we know the De Morgan's law. By applying the De Morgan's law, I can also write this one as x complement plus y complement. Similarly, this also I can write it as x dot, according to the De Morgan's law, x complement dot y complement, because x plus y whole complement, I am expanding this by applying the De Morgan's law. So NOR gate expression can also be x bar dot y bar, whereas NAND operation, NAND expression is also given by x bar plus y bar. So this is the NAND gate. Now coming to the exclusive OR gate. So exclusive OR gate, in short we can also call it as XOR, that we can also write it as XOR. is a digital logic gate that accepts more than 2 inputs but only one output value. So even this gate also can have more than 2 inputs, but the minimum number of inputs required are 2, and it produces a logic high. That is the output when any one of the input is high, then the output of the XOR gate is high. If both the inputs are high or low, then the output of the XOR gate will be 0. That means if both the inputs are same, that is either 0 or 1, then the output of XOR gate is 0. If both the inputs are different or any one of the input is 1, then the output of the XOR gate is 1. So based on that logic, this is the truth table. So here it is, I am considering a 2 input XOR gate 0 0 0 1 1 0 1 1. So when both the inputs are 0, the output is 0. When both are different, 0 1, it is 1, 1 0, it is 1, and again both the inputs are same, 1 1, it is 0. So this is the symbol of exclusive OR gate, and the Boolean expression for exclusive OR gate is given by, so the exclusive OR operator is represented as X XOR Y, where plus inside a circle represents the XOR operation. So here, now this XOR operation can also be written as X bar Y plus XY bar. So this is the Boolean function for exclusive OR gate, X bar Y plus XY bar, and we can also represent this as a plus inside a circle is nothing but XOR operator. Like plus is OR operator, right? Dot is AND operator. So similarly, we have plus inside a circle is XOR operator. Now coming to the exclusive NOR. So exclusive NOR is also, in short, we can also call it as XNOR. Okay, it's a digital logic gates. Again, it accepts more than 2 inputs and only one output. Coming to the operation. So the XNOR gate produces the output as high when both the inputs are same, that is either equal to 0 or equal to 1. The output of XNOR gate is 1. And if both the inputs are different, the output of the XNOR gate is 0. So when both the inputs are same, the output of the XNOR gate is 1. Either it is 0 or 1. When both the inputs are either 0 or 1, the output of the XNOR gate is 1. And when both the inputs are different, or else if any one of the input is 1 and the other input is 0, then the output of the XNOR gate is 0. And this is the symbol. XNOR is nothing but not of XOR. Not of XOR. Means XOR with a bubble will indicate the XNOR gate. So that is complement of XOR is nothing but XNOR. So this is the symbol here. This is the symbol of XOR gate with a bubble at the output side, which is nothing but the symbol of XNOR. Now coming to the logical operator, Z is equals to Y. So where dot inside a circle represents the XNOR operator. Plus inside a circle is XOR, dot inside a circle is XNOR. So as I told you that this is not of XOR, that means we can also write this one as X XOR Y complement. So what is X XOR Y? X XOR Y whole complement, which is Z. Okay, so X XOR Y, already we have seen the expression X bar Y plus X Y bar whole complement. So now I am taking the complement of this. So by applying the De Morgan's law, so plus will be changed to dot and dot is changed to plus. So here X bar Y whole complement dot X Y bar whole complement. Now I am expanding this X bar whole bar, that is X plus Y bar into X bar plus Y. So now if I expand this, what I'll get? So the expansion I am writing here, Z is equals to X into X complement plus X into Y plus X complement Y complement plus Y into Y complement. So as we all know that XX complement YY complement becomes 0. So the final expression for XNOR is XY plus X bar Y bar. This is XNOR operation. X XNOR Y. Okay. So this is the Boolean expression for XNOR gate. So these are all the various logic gates. And now coming to the universal logic gates. So the universal logic gates is a gate, or else universal logic gate is a gate which can implement any Boolean function without need to use any other gate. So that means without using any other type of gates, we have so many types of gates, we have seen. Without using any of the other types of gates, we can implement all the other Boolean functions with that gate. And the NAND and NOR gates are said to be universal logic gates, where we can implement any other Boolean function without need of any other logic gates, using only NAND or NOR gates. So that is why we are calling this NAND and NOR as universal logic gates. And this is advantageous since NAND and NOR gates are economical and easier to fabricate. So as these are easier to fabricate when compared to all the other logic gates, all the digital ICs will be, digital logic families will be using this NAND and NOR gates only. Next, the AND gate is a typical, an AND gate is typically implemented as an AND gate followed by an inverter, not the other way around. So we can implement an AND gate by using an AND gate followed by by using a NOT gate followed by an AND gate, so that I can implement AND gate. Likewise, OR gate is also typically implemented as a NOR gate followed by an inverter, not the other way. So as the major advantages of universal logic gates is we can implement any of the Boolean function without use of, or else without need of any other gate type using NAND and NOR. So that is why we are calling this NAND and NOR gates as universal logic gates. And these are even economical and easier to fabricate, and most of the digital logic families use NAND and NOR gates. Now, as I told you that we can implement any other logic gates using NAND and NOR. Now, let us see how to implement, how many NAND gates are required for implementing AND or NOR using NAND gates first. Okay. So, first of all, I want to implement a NOT gate using NAND gate. So, what is a NOT gate? Actually, the NOT gate symbol is this one. So, if I give A as input to the NOT gate, A bar will be the output. Now, how can I implement this one using a NAND gate? So, NOT gate is a single input gate, whereas NAND gate is a double input gate. Minimum number of inputs required for NAND gate are 2. So, what is a NAND gate symbol? NAND gate symbol is this one. And coming to the output, AB, if AB are the input, so A dot B whole bar, or else I can also write this one as A bar plus B bar, right? So, now, using this, I want to implement the NOT gate. So, how can I implement? So, just tie both the inputs of the NAND gate together and apply the single input which is to be complemented. So, as I want to complement A, so I am tying both the inputs of the NAND gate to A, so that the output will be A bar. How can I get A bar here? So, because both the inputs are A, so A dot A whole bar. As we all know that according to Boolean algebra, A dot A is equals to A, so that is A complement. So that means I can convert a NAND gate as an inverter simply by connecting both the inputs of the NAND gate together to the input which is to be complemented. So this is NOT gate implementation using NAND gate. Now let us discuss how to implement AND gate using NAND gate. First of all, what is an AND gate? AND gate is this one. If I give 2 inputs, it just produces the logical multiplication, that is A dot B. So let us consider Y is equals to A dot B. Now I want to implement this one using NAND gate. So if I take a NAND gate, so what is the output I'll get? AB are the inputs here. So the output will be A dot B whole complement. But what I require A dot B only. So if I give it to an inverter, then I'll get A dot B bar whole bar, which is equals to AB. But my aim is to implement AND gate using only NAND gate. No other type of logic gates are required. So I should replace this inverter with again NAND gate. So that is why I am using one more NAND gate where two inputs are tied together. So I am applying AB here. So I will be getting A dot B whole complement. It acts as inverter. So finally the output of this inverter will be A dot B. That means for the implementation of AND gate, I require two NAND gates. I require two NAND gates. Okay. For implementing a NAND gate using NAND gate, I require two NAND gates. Now coming to the third one, OR gate. Third one is OR gate. So OR gate, what is our symbol? Symbol is this one. Coming to the logic function. So this can be represented as A plus B. This can be represented as A plus B. So now I want to implement this one using NAND gate now. So for that, if I take an inverter, okay, two inverters here. So where A, B. So what is the output of these two inverters? A bar, B bar. So now I am giving these two a NAND gate. So what is the output I will get? I will get A bar dot B bar whole bar. Because it is a NAND gate, multiplies and inverts. So now what is expand this one by applying De Morgan's law? A bar whole bar, dot will be changed to plus and B bar whole bar. So A bar whole bar is nothing but A plus B. So that means I have to use inverters before the NAND gate. So again, I don't want to use any other gate. So I want to use only NAND gate. So replace these inverters with again NAND gate. So here, this is the implementation of OR gate using NAND gate. So this is the implementation of OR gate using NAND gates where y is equals to A plus B. Where y is equals to A plus B. So that means for implementing an OR gate using NAND gate, I require three NAND gates. I require three NAND gates. Okay. So this is the implementation of AND OR invert using NAND gate. Similarly, now let us see the implementation of, as I told you that NOR gate is also said to be universal. So now let us see how to implement a NOT gate using NOR gate. So NOR gate, what is a NOR gate? So this is the NOR gate. Okay. So if A and B are the inputs, then y is equals to A plus B whole complement, which I can write it as A bar dot B or else A complement dot B complement. So NOT gate. So as you all know that NOT gate is A and the output is A complement. So again similar way to the similar to the NAND gate implementation, I have to take an OR gate where both the inputs are tied together and the input which is to be complemented is given as input to the NOR gate. Then the output will be A plus A whole complement, where A plus A according to the Boolean algebra is also equal to A and it is A complement. Now let us consider OR gate. How to implement OR gate? So OR gate symbol is this one. So here the output of the OR gate is A plus B. So now I have NOR gate. So what is the output of a NOR gate? If I give A and B as the input, then A plus B whole bar. So what I have to get? I have to get A plus B only. So for that I am using a NOT gate again here. So that A plus B complement whole complement. So which is equals to A plus B. So that is what we need to do. Again, I don't want to use inverter. Even that inverter should be replaced with NOR gate. So this is the NOR gate again. So this is my output. So that is A plus B whole complement and this one is A plus B. So that means in order to implement an OR gate using NOR gate, I require two NOR gates. Whereas in case of NAND gate, how many gates were required for implementing OR gate using NAND gate? Three NAND gates. But here, two NOR gates are enough. Now coming to the third one, AND gate. So as we all know that AND gate is, the symbol of the AND gate is this one. So AB. So y is equals to A dot B. So now I want to implement this one. So again, the same logic I have to use. I am using an inverter at the input, both the input side. Sorry, this is a NOR gate I have to use. So here now I'm using a NOR gate. Okay, so now what is this one? Before applying it to the NOR gate, the inputs are getting complemented. So A bar, B bar. So A bar plus B bar whole bar. Now apply the De Morgan's law. So A bar whole bar plus will be changed to dot and B bar whole bar. So it is equals to A dot B. So that means I can have this kind of implementation for implementing AND gate using NOR gate. Even I don't want to use inverter, so just I will replace the inverter with NOR gate again. Okay, because I want to implement everything using NOR gate. So even the NOT gates are also should be replaced with NOR gate. So this is my implementation. Y is equals to A plus, sorry, Y is equal to A dot B. So for implementing an AND gate using NOR gate, I require 3 NOR gates. So like that, not only the logic gates, I can implement any other gates using NAND and NOR. So, and what about XOR and XNOR? So if you see the XOR and XNOR, so already we have seen the XOR gate. So what is the expression for XOR gate? X bar Y plus XY bar. So if I draw the logic circuit for that, this is X bar Y and this is again X Y bar. This is an OR gate. This is X Y X Y. So this is X bar Y and this one is X Y bar, and finally the output is Z is equals to X bar Y plus X Y bar. So if you observe this circuit, it is a multi-level circuit. This is one level of gates. This is one level and this is one level. This is one level. So I'm using first inverters. This is the first level, level 1. And the inverters outputs are given as inputs to the AND gates. So this is second level. And the AND gates outputs are again given as input to the OR gate. This is a third level. So that means this kind of circuit where the output of one gate is given as input to the other gate is called as multi-level implementation. Such types of multi-level circuits can be implemented with some procedure. So that implementation is called as multi-level NAND or NOR implementation. That means we need to go through the procedure of multi-level NAND or NOR implementation for implementing this XOR and XNOR, which I will be discussing in some other lecture. So this is, that means any other Boolean function which is a multi-level implementation can be done with the implementation procedure of NAND and NOR by using multi-level implementation of NAND and NOR logic. We have to realize them using NAND or NOR gate. So that is why I am not discussing this XOR and XNOR, which comes under multi-level NAND or NOR implementation. I hope it is clear why I am calling it as multi-level, because the output of one logic gate is again given as the input to the other logic gate in the same circuit. So that is why it is called as multi-level. So we need to go through some procedural steps in order to realize this multi-level AOI logic. We are calling it as AOI logic. What is this AOI logic? AND or invert logic. So I am using AND or NOT gate. So this multi-level AOI circuit can be implemented using NAND or NOR with some procedural steps, so which I will be discussing in multi-level NAND or NOR realization. So this is about logic gates and universal logic gates, and why the NAND and NOR are said to be universal logic gates, and how can we implement AND or invert using NAND and NOR gates. That is what we have seen. And now coming to the advantages or else uses of logic gates. So logic gates are utilized in a variety of technologies. These are components of chips, that is ICs, which are the components of computers, phones, laptops and other devices. That means, for example, we have a computer. what we have majorly various units like memory unit, next arithmetic and logical unit. So like that we have so many subsystems, right? So all those are again implemented using logic gates. So not only computers, even phones we have memories, even we have various slots that they like power supply units like that. So everything will be implemented using logic gates. So every digital circuit is implemented with logic gates. And logic gates may be combined in a variety of ways, and a million of these combinations are necessary to make the newest gadgets, satellites, and even robots. Simple logic gates combinations can also be found in burglar alarms, buzzers, switches, and street lights. So these are all the applications of logic gates where we can use this, because these gates can make a choice to start or stop based on logic. They are often used in variety of sensors. Even in sensors also we can use this logic gates. And the logic gates are also important in data transport, calculation, and data processing. Even the transistor to transistor logic and CMOS circuitry make extensive use of logic gates. So that means we have TTL logic, CMOS logic. So in all that logics also we are using the logic gates. So these are all the uses of logic gates. That means every digital circuit or its digital system is built based on the logic gates. So this is how we can find so many applications of logic gates in so many areas. So I hope it is clear to you all. So the thing is, we need to remember the operation, the symbol, and the truth table of each and every logic gate, so that we can implement any other digital systems easily. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.